Okay, let me just make sure. Good. Okay, so you have a lot of sections to read this week. You have like 5 or 6 sections. There's a lot. Yep. And slope is kind of touched in several sections. So I'm kind of touching on stuff that's in sections 1.3, 1.4, and 1.5. And I'm sort of taking a broad overview, doing a sample of types of problems you'll see with slope. But it's not going to be like every possible thing you can see, but just to kind of give you a broad overview of how these parts connect. So you can see that, 1.3 is where it specifically talks about slope, but you actually kind of hit it in 1.4 and 1.5 as well, just different formats. So that's sort of, kind of my goal here is just to kind of connect these things together.
Okay.
So first off, we need to start with a linear equation because that's where slope sort of appears. Mm-hmm. So we have the form ax plus by equals c. And so that's what we call linear equation. It's linear because there's no exponents on the variables. The exponents would essentially be 1. And when you graph it, it makes a line. So when you think of a graph, that essentially means there's infinite solutions because you've got 2 variables and you've got, any point on that line is a solution to that line. So it's different from if you have just x, you can get a single number. If you've got 2 variables in one equation, you can have infinite solutions. And this is something that actually is really important in week 2 when we talk about systems of equations, because when you have more than one equation, that's where you can solve linear equations like this and then get a single solution, but you have to have more than one equation. Mm-hmm. So this is sort of an important concept to connect this week to next week, especially because next week with systems, we usually have our equations in standard form, which basically means your x and y are on the same side. So this is the most common form that you'll see when we're using systems of equations. And in week 3, we go into matrices and they have to be also in standard form. So this will sort of connect to those 2 weeks. There are 2 other forms. There's slope intercept form, which is usually used for graphing, and that's y equals mx plus b. And then point slope form, which is y minus y1 equals m times x minus x1. And that's used mostly for writing equations for a line. Now, the slope in both of these is the letter m. So this is where we get us to the idea of slope, because you can't get an equation for a line unless you know what the slope is. So you always need the slope first before you can get your equation. Okay. So slope is a number. Sometimes it has units, sometimes it doesn't. It depends on what you're looking at, but it is indicating how slanted a line is, as well as the direction of the line. And one thing that is really important, that it is not the same thing as the angle between a line and like the horizontal or 2 different lines. It's not an angle. In week 6 and 7, a lot of people get that confused because we'll start talking about angles and then we bring in slope back again from the beginning of the class. And so it's very important to remember that these are actually not the same thing. You can have a line with an angle, but they're not the same. So the number for the slope, the actual value, tells you how steep the line is, and the larger the number, the steeper it is. And when you look at this, you ignore the sign because the sign is telling you the direction. So a slope of -2 and a slope of +2 have the same steepness because the actual value, the number, is 2. So you're kind of looking at the absolute value. But a slope of -10 versus +2, the -10 is steeper because 10 is bigger than 2. Now that negative sign, so slopes are positive or negative, that is just telling you as we move left to right, are we going up or are we going down? Are we increasing or decreasing? And that's what I mean about direction, is it's just, are you going up or down on the graph? So positive slopes are always going up, you're increasing in value. So we always read graphs from left to right. So you're moving up as you go left to right. And then a negative slope means you're decreasing. So you're going down as you move left to right. So they're in total opposite directions if you have a positive slope versus a negative slope.
Okay.
So the equation for slope, so we use the letter M for whatever reason. And so there's lots of ways to write the equation. You'll hear rise over run, which is rise is how high it's going, and then run is how far over it's going horizontally. And that is basically asking how much is it changing in the Y direction divided by how much is it changing in the X direction. So it's a ratio here because you're looking at the change in one direction divided by the change in the other direction. The phrase change in is uses actually the Greek letter delta. So that's that triangle looking thing. That's actually the Greek letter delta, and that is representing change. So you'll see delta Y over delta X, and that means change. And that symbol is used a lot when you move on to calculus. So this is called pre-calculus for a reason. We're introducing things for calculus. Right. So if you know you have to take calculus, you're going to want to make sure that you know what that symbol means, because you will see that again. And then if we actually say, well, what does it mean to have the change? It's the difference in the Y values divided by the difference in the X values. And so we have that as Y2 minus Y1 divided by X2 minus X1. Now, the order that you do the subtraction doesn't matter as long as you have the same ordered pairs, like you're matching up the points first and last. So you could do Y1 minus Y2, but then you would also have to do X1 minus X2. You can't do Y1 minus Y2 and then X2 minus X1 because they're in reverse order. So you just have to make sure that you line them up, but it doesn't matter whether it's 2 that's first or 1 that's first, as long as you're consistent.
Right.
So I already talked about kind of the steepness there and whether it's positive or negative, what that means. You can also get values of undefined, which is when you're dividing by 0. So that means there's no change horizontally, so it's a vertical line. And then, and I call this infinite slope because it's like it's as steep as it could possibly be. It can't be as, it's infinite steepness, but just to be very clear here, because I have this in parentheses, infinity is not the same as undefined. So that's why it's in parentheses, because technically the slope is not infinity. It means undefined, and this is because we don't have a way to divide by 0. It's not part of the mathematical definition. So that's what undefined means. Then you can also have slopes of 0, which means that you have to have 0 on the top of the fraction. So that means there's no vertical. So it's only a horizontal line. And so it's basically flat. There's no slant to it at all. So a lot of conceptual stuff here.
Excuse me.
Okay, so this is kind of rephrasing some of that, what it would look like, and then connecting this to the actual equation of a line. So as long as you have a slope that's slanted in some way, you have your equation for a line, the ax plus by equals c. If it's a horizontal line, then that slope is 0 and your equation is y equals, you don't have x values in your equation at all. Because the x, you've got all x's, but it's really only going through a y point. Mm-hmm. And then when you've got a vertical line, you've only got x values. You've got that 1 point through x that it's going through, and then there's like infinite many y. So your equation only has an x value. And then we often compare lines. So we'll have parallel lines, we'll have perpendicular lines, and then ones that are not one of those can intersect, but they're, not in one of those. So these connect to slope because parallel lines have the same slope. So that is key to determine if lines are parallel, is you look at their equations and then figure out the slope. Or if you have two sets of points, you find the slope.
Okay, so I'm sorry.
Go ahead.
You've got same steepness, same slope. So I'm trying to differentiate between the two. Of
So
steepness and
this,
slope.
yeah, steepness is not including the sign. Because they could also be, they could both be, you know, either negative or positive. When we think of steepness, we're just looking at the numerical value without the sign involved. The
Okay,
slope is including the sign.
okay. Got it.
Yes, so
Makes sense.
that's why they're a little different, because you could have a steepness of 2, but then the slope is actually -2 because you're just looking at the number. Yeah.
Right, makes sense.
Yes. So perpendicular lines, they're going in opposite directions. So their signs have to be opposite. So one's a positive number, one's a negative number. And they intersect in such a way that they form a right angle. So that is 90 degrees right here.
Mhm.
And when you look at their slopes, if you multiply their slopes together, you get -1. And this is a concept that is really important once you, with some trigonometry, some calculus, and you start doing things with vectors, and you have things that are called orthogonal, and that's basically meaning perpendicular. And so you have these things involving trig where you get a result of -1, and that's saying that it's perpendicular. But we use the term orthogonal when it's more than just lines, but that's something that will show up again. So this is sort of like kind of introducing you to that concept here.
Right.
So their slopes multiply to -1. And then if you just solve that equation, if you have one slope, the other slope is the negative reciprocal of it. So it's opposite of sign, and then it's the reciprocal. And then that's how you can determine the slope of the other line.
Okay.
And then you've got slopes that are lines that don't fit into either of these two categories. And so their slopes are different, their steepness is different, they intersect. There's no relationship from one slope to the other on the two lines. They're just not related.
Mhm.
So this is just to kind of rephrase that, so that in case some people, you know, this might get kind of lost and they're trying to find their perpendicular lines and all that stuff. So, okay, so this here is where we start connecting things to calculus and what you're going to need in calculus. So generally, when we talk about slope, we talk about slope of a line, but you can use the same concept even if you don't have a line. So I could have a polynomial, say it's looking something like this. It's curvy, you know, definitely not a line. And I could say, I want to know how these 2 points are related. And so if you were to draw a line between those 2 points, that's what we call the secant line. Is the line that goes between those 2 points. And there's another, when you get to calculus, there's another concept called a tangent line, which is slightly different. But the secant line is just if you have any 2 points and you just connect them with a line. So now you have a line and you can use the slope of that to do some approximation. And so if you find the slope of this line, that is called the average rate of change. It's basically the average amount of change between those 2 points. So it's literally just the slope formula, but we write it in function notation and without the letter m because it's not a line. But it's the same formula. You're taking your y values, subtracting them, and then dividing by your x values.
Okay.
Then we have what is called the difference quotient. And again, this is very similar. And how this one is you have, let's say I have some point right here, and then you pick another point close to it. And if I, you know, create a line, it's very close. And the distance between those points we call h. And so you have a point of interest, and then you're looking some distance away from it. And usually h is pretty small. And that's what gives us a tangent line here.
Mhm.
So the tangent line is a line that when you get really close to the point, it looks like it follows the graph, even if it's not a line itself. Like this is not actually a line, but if you have points close enough together, you can make it look like a line. So that's what's called the tangent line. And that's where we use the difference quotient. So you're just picking another point that's close to it, some distance h, usually small. And then again, you're finding the slope between those. And so you've got your, it's f of x plus h. That would be basically the h distance away gives you your second point minus your first point. And then when you're dividing by the difference in those x values, that difference is h because we chose it to be h apart.
Okay.
So that's something that's used in calculus. And that forms the basis of what is called the derivative, which is basically half of calculus. And so these are all basically taking the concept of slope and then expanding it out to things that aren't lines and calling it different names because they're not technically lines. And I just got another chat of someone asking for me. So hold on. Okay, just letting them know I am busy. Apparently I'm popular today. Are there any questions so far?
Nope, just taking it in.
Okay. So now I'm going to just start going through examples, and we're going to just start from the stuff with lines, and then we'll move our way to the average rate of change and the difference quotient. So you'll see how all of these kind of, all of this gets used and the different ways that you could be using slope. So first, I'm going to write the equation for slope here. y2 minus y1 for x2 minus x1. So we want to find the slope of a line passing through x2 negative 1 and negative 2, 1. So these are two ordered pairs. And we want to label them as our x1, y1, x2, y2, which apparently I wrote 2 twice there. And it doesn't matter which one you label in which way. So I usually just label the first one and as x1 and y1, and then the second one is x2 and y2, and your ordered pairs are always x comma y. So once you identify those values, all you need to do is plug it into your formula. So it's y2 minus y1. So I've labeled y2 as a 1. And then y1 is a negative 1. So I need to have parentheses around it so that you don't get lost with those negative signs. Because you've got minus and then a negative. And then in the denominator, we've got x2. So that's negative 2 minus x1, which is 2. So when we're subtracting a negative, we're adding. So when I do the math here, I get 1 plus 1, which is 2. And then negative 2 minus 2, which is negative 4. And then we don't like to give our slope as decimals unless it's like a word problem. We leave it as fraction form. So we want to reduce this here, and I can reduce it to a negative 1/2 just by dividing the top and the bottom by 2. And then that's the slope. So what this tells us is that if you were to connect these 2 points with the line, it's negative, so it'd be decreasing as you move left to right. And then a 1/2 slope is, it's a small value close to 0, so it's going to be pretty flat. It's not going to be very steep because 0 is horizontal. So I'm going to pull up a browser here. So there's a graphing calculator that I recommend that you learn how to use, which is Desmos, DESMOS, and then you just hit graphing calculator. So what you can do is I want to just kind of move this over here. Oops. I want to graph these 2 points, and then we're going to connect it with a line so you can kind of see the slope. So in order to do that, I hit the plus here, and then I can put a table of values, and then I can type in my ordered pairs. And then to make them connect with the line, you click and hold on the color part here, and then you just turn lines on. So it's connecting them with a dot, and you can see that this confirms our slope was negative, so it is going down as we move left to right. And then it's not really steep. In this view, it's looking, like a 45-degree angle here, something here, but it's got a slope of -1/2, and so that's what that looks like. So this second example here is, now we've got a different slope. Use the slope m equals -2 and the point 0, -9 to find 3 additional points through which the line passes. And so this is a nice thing that you can do with slopes. So we have m equals -1/2, or not 1/2, m equals -2. Got to read the right number here.
So what is this function called? So the first one was we were finding the slope. Now, what would you call this operation?
It doesn't really have a specific name. It's just I guess you could say it's using slope to find more points. That's
Okay,
the best
okay.
way to describe it.
Okay.
It's a good concept to see what slope means, basically, and then connect it to a graph. So you'll see we'll graph it after we do this.
Okay.
So if you get a whole number slope, you can always make it a fraction by writing it as -2/1. And we're going to relate this to the change in y over change in x. So this is telling us our change in y is a -2 and change in x is 1. So if you're given a point like 0, -2, we can subtract 2 from the y and add 1 to the x coming from our change in x and change in y there, and that will give us a new ordered pair. And so if we have a line that has these properties, 1, -11 is also going to be on that line. And then you can just do this again as many times as you want to figure out more points on the line. So again, my change in y is -2, and I'm adding 1 in x, and then this can give me 2, -13 as another point on that line.
So where did you get the 1? So you got the, I know where you got the -2.
So
But then you get the change of 1. Where'd you get the 1? For
that's
the
coming
change of X?
from. So if you have a whole number, you write it as a fraction. So you're taking your slope, and it needs to be in fraction form in order to use this property, this rule.
Okay, now, okay. So you
Yeah.
converted the whole number into a fraction form. Okay, I got
Yes.
it.
Yep.
Okay. I'm with you.
So another way that you can do this is, let me go back to this. Yeah, go ahead.
I'm sorry, I have a question.
Yeah.
Where did you get I stepped away for a minute, but where did you get the 11 from? That -11?
That's from -9 minus 2. So since the change in y is -2, I subtracted 2 from the y value of -9, and that gave me another y value, -11.
Okay, so you added it, but it's okay.
Yeah. So I can kind of color code here.
And it still remains a negative?
Yes.
It's two negatives.
Yep.
Okay. All right.
Okay, so if we go back to our slope, I have -2, but a negative sign, if you have a single negative sign, it doesn't have to be with the top part of the fraction. It could also be on the bottom part of the fraction. So I could instead subtract 1 and add 2. So I can flip where that negative sign is. And that's like you're finding the slope backwards. And that will also give you a point on the line. And that will give us -1, -7 there.
Mhm.
So the slope allows you, if you have a single point and you know the slope, you can move in either direction on that line. You just have to make sure that you're consistent with your signs if you've got a negative slope. If it's a positive slope, you'd either both be adding or both be subtracting in order to make them equivalent.
Okay.
So then you'll be graphing at -1 and -7, correct?
Yes. Yeah.
And that's the answer to your
Yeah.
question?
So yeah, the problem is asking for 3 additional points that would be on this line. And so we've just found 3 of them: 1, -11, 2, -13, and -1, -7. So I'm actually going to graph those.
Wow.
And I'm going to make a new table to graph these values. So our original point was 0, -9. And then we got 1, -11, 2, -13, and then that third one is a -1, -7. And so I can connect these with a line, and you can see that these are all on the same line. They're all in line with each other. And so that slope of -2/1 is basically saying I'm going down 2/1 and I'm on my line. Down 2/1. You can keep following this pattern, and that will allow you to extend your line out and keep finding new points that would be on this line if we connected the line out in either direction. Now, I'm not going into writing equations for lines, but this would be the equation for a line. So for this particular line. And so I can pick any location on here and use that slope of going down 2/1 and get another point on here. Like I can be right here, I go down 2/1, I'm back on the line. So that's what that slope is. It's just, and you can either go up 2 and over 1. That's what we did when we were doing the opposite side, up 2/1, up 2/1. So anywhere on this line, you can get new points from it. If you know one of them, you can use the slope to get another one. Okay, so here's an example where we're going to be looking at the parallel, perpendicular, and neither. So we've got 2 lines here, just L1 for the first line, L2 with the second line. And we want to know if you were to graph these lines that have these ordered pairs, are they going to be parallel lines, perpendicular, or neither one of those? And so we do this by comparing the slope. So you need to find the slope of the first line and the slope of the second line, and then we're going to compare that. So the slope of the first line, we're going to call L1 or M1 because it's L1. So we'll just use the same labeling. And so again, the equation for slope is y2 minus y1 over x2 minus x1. So I'll use the second ordered pair as my 2, first one as my 1. So y2 is 5. And then y1 is -1. And then x2 is 1, and x2 is -2. So it's coming from the 2 ordered pairs listed for L1. We had -2, -1, and 1, 5. So 5 minus a -1 is 5 plus 1, so we get 6. 1 minus a -2 is 1 plus 2, which is 3. And then that simplifies to 2. So that first line has a slope of 2. And so it's going to be approximately looking like this. It's positive, so it's going to go up from left to right.
Mhm.
So now the second line here, we have ordered pairs 1, 3 and 5, -5. So y2 is -5 and y1 is 3. And then x2 is 5 and y1 is 1. So that gives us a -8/4, which is a -2. So this graph, or this is going to be
Yeah, the
going down from left to right. So parallel lines mean that slopes have to be the same, but these numbers are not the same. One's a +2, one's a -2. So these are not parallel. So you'd say that M1 does not equal M2. So they are not parallel. For perpendicular, they need to multiply to -1. So M1 times M2, if you were to multiply these numbers, you would have 2 times -2, which gives you a -4. And this is not equal to -1. So because they don't equal -1, they're not perpendicular. And so that means that these lines are neither parallel nor perpendicular.
When you plug in on M2, when you plug in your -5 and your -3,
Mhm.
I see up top, how it's in the brackets, but how do you know which where to put it for the Y2 and the Y1?
So
You understand my question?
you just decide which point is going to be 1, which point is going to be 2. So I always decide that I always make the second point 2. So it's always going to be this value minus that value. So I always take the second value minus the first value.
Okay.
And then
so does it have to be like that, or it could be any order? You still get the right answer.
you could do it 3 minus a -5, but then you have to do the same order 1 minus 5. So if you
Okay.
do it the other way around, you have to be consistent and do that same order on the bottom.
Okay. So can you just explain, I'm sorry, how you do it again?
So I'm taking my second point, the -5 minus 3. So that second minus the first. And then you look at the other pair values. And you do 5 minus 1.
Okay. Got it. I got it.
Yeah, so I don't know if this is helping, but I take this value minus this value, then this value minus that value.
Okay.
And then you always have the y values divided by the x values.
All right. Thank you.
Mm-hmm.
Can you go over the not perpendicular? You got M1, M2 equals -4, not equal to -1.
Yeah. So for them to be picked perpendicular, they need to multiply to -1. But we have values of 2 and -2, which give us -4.
Got it.
Yeah. So we're multiplying those. And so -4 is not the same thing as -1. We need it to be -1 if they're perpendicular.
Okay, that was a multiplication there.
Yes. Okay. If you see 2 letters next to each other, you assume multiplication.
I did, but I didn't want to assume it.
In that case, it's okay to assume. So I'm going to graph both of these so you can visualize. So our first line, we have -2, -1. And 1, 5. And then our second line, 1, 3, and 5, -5. And so you can see if we were to extend this line out, they don't really form a right angle, and that's why they're not perpendicular. So I wonder if there's a way that I can draw on here. Well, I know a way I can. Nope. I thought I did. I thought there used to be a way that I can. Thought there was an or maybe I do this. There we go. Okay, so I'm going to try to freehand it really badly. But if we were to extend that line, of course, now it's in the wrong color, but you can see that where they intersect, it's not a right angle. So they're not parallel because they're not following in the same direction and everything. And they're not perpendicular because it's not actually forming a right angle. It's smaller than a right angle there. So that's why they're neither. So it's always good to use slope and not to eyeball it, because, you know, if you try to eyeball, you might think, oh yeah, they look perpendicular, but the slope will tell you for sure.
Right. Okay.
All right, so here we're going to get into what slope actually means when you have it in a real world problem in real life, because it actually does have meaning once it's part of a problem and not just random numbers. So we've got two lines. We don't know what the equations are. We're just you know, got these two lines. The slopes of lines representing annual sales Y in terms of time X are given below. So we're just looking at the slope. We just have two hypothetical lines for two hypothetical products representing sales. And we're just looking at the slopes. So we want to use the slopes to interpret any change in annual sales for a 1 year increase of time. So this is basically if you have a line. And so our first example, this line has a slope of 135. Just basically, what does that mean? So if you have you're graphing your sales for some product, or the slope is positive, so that's telling us that the sales are increasing. And they're telling us this is for a 1 year increase in time. And that comes from the slope, because you have a whole number that you can always put over 1. So your amount in X, your change in X, which is change in time, would be 1. So that's for 1 year.
Okay.
And this 135 is basically meaning how much is the Y value changing, which is our annual sales. So you can take this slope of 135 and we can write it as a fraction, 135 over 1. Oops. And the top is the change in Y, bottom is the change in X. So Y, I'm assuming is measured in dollars because it's annual sales. I'm just assuming that it's going to be sales and money. And then our units for X are years, because it says it's in terms of time. And generally when we look at this stuff, we do it in terms of years. So this slope is telling us that we're increasing, because it's positive, by $135 each year. That's what this is telling us. That's how we can interpret this slope. The fraction means dividing or per. So if it says to interpret the change, you would say the annual sales increased, because it's positive, by $135, and we're just assuming dollars because it didn't give us any other information, in 1 year, because that's what we have for our change in X. So slope in real life is telling us how something is changing per year, or it's a rate. Anything that is like your salary, if you have something that's dollars per hour, that's actually a slope. If you were to write that as an equation, how much you're getting paid per hour. So a lot of things in real life are actually slopes because they're actually rates. And so they have meaning, and you go back to the units and you go back to what the problem says, and then you write a sentence. Anything that tells you to interpret means you need to write a sentence telling me what this means in context with the problem, which means include units, make it, tell me what it actually means.
I'm sorry, back up, say that again, where we need to write a sentence is when?
If you see the word interpret.
Okay.
Yes. And that will show up in week 3, there is a problem on the application assignment that says interpret. That tells you need to give a sentence. And for all of the homework problems, they're all word problems that you guys do every week. Include units in your answer, put them in context, write them in sentences, your final answers in sentences, because we're applying the math to a real life thing. So it's now going beyond the math, and we want to put it in context of what we're trying to find.
So
basically, go ahead, I'm sorry.
No, you go first.
So while I was just saying, because we just assumed that the units we knew the unit of time because that was defined to us was year, but we assumed that it was unit of dollars because of revenue or the term or annual.
Yes, exactly.
Right? But it could in theory be something else.
It could in theory be something else. And we try to be very specific on the problems to be millions of dollars or, that sort of thing. But if you're not given, just assume dollars, because that is the most common unit that we use for sales and those kind of things.
Okay, thank you.
So basically it's answered in that simple form for the first one. The line has a slope of M135. So your answer is the annual salary increases by $135 in 1 year?
Yes. Yeah. So
simple.
Yeah, we're just saying, what does that number mean in context of the problem? So to take it out of just the number, but if you were, say you were in business and you wouldn't go to your boss and be like, oh, it's 135. They'd be like, what are you talking about? That might be what your graph says, but we need to actually put it in non-mathy terms. So the slope of 0, that tells us there's no change at all. So they have not increased, they have not decreased. There's been no change in the sales because it's 0. So there's not, we would just say the annual sales have not changed in 1 year. So that's pretty simple. 0, no change. That makes total sense when you think of what 0 means.
Mm-hmm.
And then the last one, we've got -40. So that negative means we're now decreasing. And so it's going to be decreasing by $40 in 1 year. So the annual sales decreased by $40 in 1 year. So that sign is really important because that's telling us increase or decreasing. But as far as how much, the sign doesn't matter. It's not like -$40, it's $40. That sign is just telling us increase or decrease. So now we're going to move on to the stuff that's heading towards calculus, because that's why you're taking this class. You're in pre-calculus for a reason, to prepare you for calculus. So we're going to do the difference quotient here. And this is heavy algebra. It's basically all you're doing is algebra skills here. So just to refresh, the formula for the difference quotient is f of x plus h minus f of x divided by h. So we want to find the difference quotient for x equals 5. So we're going to be replacing x with 5, and then we're going to have h in our answer because we don't know what h is. So our answer here is going to be an expression with a variable in it. It's not going to be a single number. So the way that I do this is I first find each function part separately before I put them in the fraction, because if you try to do it at the same time you're in the fraction, it can get very messy. So we're looking for when x is 5. So we want to first find f of 5 plus h. So what this means is that everywhere that I have x in my function, I'm replacing it with 5 plus h. So this is a function composition. We're basically replacing x with something else. So I like to kind of color code to make that easier whenever possible, just so you can make sure that you're plugging in everything correctly. So it's 5 times x, so that's going to be 5 times 5 plus h, minus, and then x squared. So that's going to be 5 plus h squared. And now this is where we start doing the algebra, because we need to distribute, because we want to try to simplify this. So I have to multiply 5 times 5 plus h, and I have to square the 5 plus h.
Before you go any further, can you just backtrack up how you got that, written out from the first?
Yeah, so these are coming from, I'm connecting, let's see, this function here. So I have 5 plus h, so that's going in for x. And so that's also being replaced by x right here. So that's how I have 5 plus h right there. And I've got that 5. And then we're also putting it, instead of x squared, it's now going to be 5 plus h squared. So everywhere you see x, we're writing 5 plus h.
Okay. Everywhere you see x, put 5 plus h.
Yeah, this is a very important concept that will show up a lot in calculus. You'll be doing things like this a lot. So, maybe make a little bit note in your notes that when you get to calculus, you'll be doing this a lot.
And this is you said everywhere you see x, you got to put 5 plus h?
Yes.
All right.
And that's because that's what's on the left side there. So we need to start simplifying here. So I need to do 5 times 5, which is 25. And then 5 times h, so that's 5h. And then we need to multiply 5 plus h squared. So I have a feeling that I was going to use the shortcut, but I probably should show that for you guys. So you're basically doing the FOIL process for that, because 5 plus h squared means you've got 5 plus h times 5 plus h. So this stays the same, minus. So I've got 5 times 5, which is 25. And then 5 times h. Then h times 5, which is also 5h. And then h times h. So we're doing FOIL.
That was a lot right there.
Yes. Yeah, so if you need to review FOIL, you can look on YouTube, look up FOIL or multiplying polynomials. And you will find lots of videos on that to kind of refresh that skill. So we're just simplifying here. So I have 25 plus 5h. And now I need to distribute that negative. So that's a minus 25. And then I'm going to have a minus 5h. another minus 5h, and then a minus h squared. So that negative is going to everything in the parentheses. And then you start simplifying. So when we start combining like terms, we have a 25 minus 25. So that just becomes 0. So I'm just crossing those out. We have a 5h and a minus 5h. So that becomes 0. So I'm just crossing that out.
Why does it become 0? That minus 5 and positive 5.
Because 5 minus 5 is 0. So it just disappears.
Got you.
Yep. So that means we're left with negative 5h minus h squared. So now we've done that part. What we have just figured out here, this is this part right here. Where x is 5. So now we need to find the f of x, but x is equal to 5. So now we need to find f of 5. So same function, but now everywhere I see x, I'm replacing it with 5. This is where you really earn your pre-calculus stuff right here. So 5 times 5 is 25, and then 5 squared is also 25. So luckily for us, this comes out to 0. So that's really nice. It doesn't always come out to 0, but for us in this particular problem, it does. And so now we have just discovered, or just kind of found, this part of our equation is going to be 0. So I'm actually going to add a blank slide here because clearly I need more space. So going back, our difference quotient, and this is the same problem, just it's a long one. So our difference quotient formula is f of x plus h minus f of x divided by h. And they told us that we want this at x equals 5. So we have f of 5 plus h minus f of 5 over h. So on the previous slide, we found out what f of 5 plus h is equal to. So that is negative 5h minus h squared. So I have negative 5h minus h squared. And then minus, and then we found f of 5, which is 0. So I'm replacing that with 0. And then it's over h. So this gives us negative 5h minus h squared over h. And this is a rational expression, and we need to reduce it. So if you notice, there is an h on everything on top and everything on the bottom. So I can factor on the top an h out of our parenthesis, or factor out an h. And So, and usually if you have a negative in front, you also factor out a negative. So if I factor out a negative h, that gives me 5 plus h. So I just factored on top. And then from here, I can cancel out because there's an h on the top and an h on the bottom. And this gives us our final answer of negative 5 plus h. And that is your answer to the difference quotient. So you can't get rid of h because we don't know what h is. All we can do is get an expression, and this would represent that slope near 5. And then you just, if you want to get really close to 5, you can have like h plus, or maybe set h at like 0.01 or something like that. And then you would find that slope and be really close to there and kind of get what is the steepness at that particular point. That's sort of what the difference quotient is talking about, is if you just look at one point, we get really close to there, what is that steepness really?
Okay.
So I know difference quotient is a lot of steps. It's a lot of algebra. You really got to remember all of your algebra skills, because you've got rational expressions, you've got factoring, you've got multiplying, you've got function notation. It's a lot to do. And if you're going on to calculus, you end up having to really need your algebra skills. So you're going to be kind of working on your algebra skills this whole class. So that way, when you get to calculus, you'll be prepared. So are there any questions?
No, I'm good.
Okay.
I guess the only way to get better with this is just to keep practicing, of course, right?
Yes. Yeah. Math is one of those things that the only way you get better at it is doing it. It's not something that you can skip. You just have to do it, unfortunately.
Because that was a lot going on there.
Yes. Now, the good news is that, while this is really difficult here, you'll do it more in calculus. So this is just kind of introducing you to the concept, and then you'll see it again later. So it's not like this is going to be the only place and you need to be perfect at it right now, because you will see it if you go on to take calculus, and so you'll get more opportunity to practice.
Mm-hmm.
So yeah, I had another example for average rate of change, but that we've already spent an hour, and I don't want to take too much of your time and overload you. But what I'll probably do is just do the work for that one, so that way when I email out the slides, you'll at least still have the work that you can use as a reference, even if we didn't go over it into this session.
Thank you for taking the time.
Yeah, you're welcome. I'm glad that you guys were able to make it. I wasn't sure, middle of the day, but this is great. And I really appreciate asking questions, because that, it's a real class then. It's not just me talking,
Is this going to be the reoccurring time slot?
If that's what it looks like on the survey, we'll keep it at this time. So I'm going to give everybody, until the end of week 1 to see if there's more times, and then I'll pick what seems to be the most popular. But if this works for most people, then we'll keep it at this time.
So we could, I got here luckily, but so if you want to propose like a later time, like 4 o'clock, we just go on a survey and put it there?
Yes. Yeah.
All right.
Yeah, and I do record them. So like, even if you come in late, at least you'll on the recording, you can go back and see the stuff that you missed. So that's nice. You don't get to ask questions, but at least, you're just not like you're totally out of luck.
All right.
Yep. So I got to wait for Zoom to process the recording, and it will take a while, and then I upload it to YouTube. But I'll make sure to email out the video will be linked on YouTube, and then I'll email out the PowerPoint as well by today. So that way you'll have that in your email. It'll be in the class, and then you can use it as a reference when you start working through all the homework and everything.